Good morning everybody. Today we have reached almost the end stages of ore forming processes, and the title, which is combined for primary and secondary processes, is labeled as Evaporation of Brine and Metamorphism as ore forming processes. And in this we shall see how these two things sometimes make and remake ore deposits. At the outset, evaporation and metamorphism seem to be unrelated as processes of ore formation, except that both produce ores. However, there is also one similarity in them, being the end stages of the relay race of ore forming processes in natural environment, the former in the secondary and the latter in the primary environment. Chemical weathering produces deposits like residual, chemical, precipitates and supergene enriched deposits. Metamorphism, on the other hand, acts on either on rocks or ores formed by igneous and sedimentary processes, forming metamorphosed deposits or making a new one, working on the elements present in the host rock and which is referred to as metamorphic deposit. In this lesson, we will divide this joint theme under the following head. Number 1, brine, the source material for evaporite deposits. 2, typical evaporite sequence. 3, ancient and present day evaporites. 4, metamorphism as ore forming processes dealing with metamorphosed deposits, and metamorphism as ore forming processes dealing with metamorphic deposit. Module 1 deals with brine, the source material for evaporite deposits. On the basis of their salt content, waters with less than 0.05% salt are called fresh, when it is between 0.5 to 3% brackish. It is called saline when the salt content lies between 3 and 5%, and it is known as brine when it is exceeding 5%. The dictionary meaning of brine is water saturated or strongly impregnated with salt, for example, the sea water. Here we are dealing specifically with the saline water that has resulted in the secondary environment towards the end stages of geochemical differentiation, after other elements have been precipitated out or nearly so. Of course, the sea water, which is continuously fed by the rivers, is the major player. The theme of geothermal brine, which are hot concentrated saline solutions due to circulation through hot rocks and enriched in salts and trace elements, is not under consideration, nor is the hot brine solutions supplied from hydrothermal systems along the mid oceanic ridges, as also the saline droplets in the form of fluid inclusions in magmatic minerals. The main source of supply of elements to the ocean, which you will find in the PowerPoints, is through rivers, either as solutions or suspensions, as well as from the upper mantle via volcanic activity. Their removal from the ocean system is through sedimentation and biological activity. However, the abundance of common anions of seawater, namely chloride, sulphate, bromine, is far greater than what has been supplied by terrestrial weathering alone. Thus, they have been mainly the contribution of submarine volcanism. On evaporation, the constituents become more and more concentrated, but minerals produced by evaporation of seawater are not being formed on the ocean floor. It needs detached coastal lagoons, restricted seas like the Red Sea or the Dead Sea, or shallow bays, and detached sunken blocks in the arid regions lacking exit, but which are replenished steadily as the evaporates were steadily accumulating, which is also represented in the PowerPoint. This is suggested by the presence of thick evaporite deposits in many parts of the world. Evaporite deposits are characteristic of the arid regions of the world where evaporation exceeds the inflow and there is no scope for exit for the saline waters. It goes without saying that many huge salt deposits of the world presently are situated in different climatic conditions, and therefore, their presence there speak of warm and arid climate as also favorable geological cum tectonic setup at the time of their formation in the geological past. Considering what evaporite minerals are there, the answer is the list of evaporite minerals is long. There are around 80, of which a dozen of them are fairly common and 3 of them predominate: halite, which is sodium chloride, anhydrite and gypsum, which are calcium sulphate. Mineralogy of marine and non-marine evaporite deposits is somewhat different. Marine evaporites are grouped in 3 classes: chlorides, sulphates and carbonates. The main members of the list are presented in the PowerPoint. No marine evaporite minerals are to be found in the marine ones. Sulphates and carbonates of magnesium, sodium and calcium predominate. Some of the non-marine includes epsomite, thenardite and borax, among others. Even sulphur is derived due to bacterial action of gypsum in the salt domes. In module 2, we shall see typical evaporite sequence. Over the geological past, ocean waters has reached a state of chemical balance between supply and removal of elements present. There are 2 main sources of supply: material supplied by terrestrial weathering through transportation by rivers, and second, from the interior of the earth by the expelled gases and fluids during volcanic phenomena. This is especially true for common anions like chlorine, sulphate and bromine, which could not have been supplied simply by terrestrial source. Interestingly, evaporite deposits do not form presently in the deep ocean floor, because seawater is not saturated with these salts. It is only when seawater is walled up in a shallow coastal lagoon, lakes, inland seas, coastal sediments of the arid regions with periodic replenishment of such saline waters that the deposition of various salts materializes. Salt deposition from such evaporating salt water is not a haphazard process. There is a definite sequence in which these salts appear and are related to the degree of evaporation affected. Based on the theoretical and practical work of various scientists, especially Phillips from 1947 onwards and later works, salts that are least soluble naturally reach their saturation first. and sequence of precipitation is not controlled by the abundance of a particular salt in the sea water, but by its solubility. Calcium carbonate is the first solid to separate, followed by dolomite, though not many dolomite have been formed in natural environment in this way. It is estimated that 1,000 meter of enclosed seawater on evaporation will not yield calcium carbonate more than few centimeters. When evaporation reduces the original volume to 19%, then only calcium sulphate will precipitate. To begin with, gypsum, while anhydrite appears only when nearly 50% of calcium sulphate has been deposited. When the original solutions has reduced to a state of 10% of the original, sodium chloride begins to precipitate. With further evaporation going on, complex potassium, calcium and magnesium salts, which we call polyhalides, are precipitated. Pure magnesium and potassium salts need extreme evaporation conditions, which is 1.54% of the original volume. The whole sequence is illustrated through PowerPoints. The order in which salts get precipitated is controlled by a number of physiochemical factors, including concentration and solubility of salts, temperature of the solutions and the presence of other salts. A number of environments and models for evaporite deposition have been suggested. Environments include non-marine environment, shallow marine environment and deep marine environment, and models suggested include deep water, deep basin model, shallow water, shallow basin model and shallow water deep basin model. Many detailed aspects of the origin of evaporite deposits in different environments are beyond the scope of this lesson. It will suffice to say that special geological condition existed to form the thick and voluminous salt deposits in the past, but the basic requirement of their either ancient or modern evaporite is a relatively arid climate, rate of evaporation exceeding the rate of inflow and the absence of any exit from the basin of evaporation. In module 3, we shall see ancient and present day evaporites. Evaporite deposits are of two types: ancient evaporites and present day evaporites. Marine evaporite deposits are common occurrences right from the late Precambrian to the present times. USA has probably the largest number of ancient evaporite deposits in the world. It occurs throughout the geological column from Ordovician onwards. Their thickness reaches hundreds of meters. Upper Silurian gypsum beds in the Great Salt Lake region is over 450 meter thick. Carbonaceous anhydrites in Utah, Permian evaporites of New Mexico and Central Texas, Cretaceous beds of South Central Florida are even thicker. Permian salt beds of Northeast England is at least 450 meter thick with zones of halite, potash, carbonates and anhydrites. Pakistan has one of the best salt deposits in the Salt Range area. Huge deposits are found in Siberia, Iran and several other parts of the world. One of the most famous Indian occurrence of evaporite deposit is from the Mandi area of Kulu Himalaya in Shali belt of post Paleozoic age. Rock salt is the main mineral and the deposit has similar features to that of Pakistan. Gypsum is the next major evaporite deposit of India, for which tertiary deposits of Rajasthan including Bikaner, Nagaur, Jodhpur, Jaisalmer, Suratgarh, Dholeria among others are presented in the PowerPoint, and Eocene to Pliocene deposits of Gujarat in Junagadh, Porbandar, Rann of Kutch are more famous. Himachal Pradesh, Jammu and Kashmir, Tamil Nadu and Karnataka also have a number of evaporite deposits. Present day evaporites are various saline deposits of salt lakes and inland seas. Many of these sites are those which have lost their original oceanic connection, and the extreme arid or semi-arid conditions leads to evaporation and deposition of salts. Dead Sea, Lake Essel in Djibouti, Great Salt Lakes of Utah, Lake Carson in Nevada, Lake Elton of Russia, Lake Urmia of Iran, Lake Damoshakova of Siberia, Caspian Sea, Persian Gulf and various lakes in Rajasthan, India including Sambar, Didwana and Pachbhadra and Lukun Ansar are good examples of modern day evaporite deposits. Evaporite deposition at Deep Springs Lake, California, which is fed by springs, is shown in PowerPoint. Apart from these, playas in arid regions and marine salt pans on different islands like Bahamas and Cyprus are also good resources of evaporites. Dead Sea in the north of the Great Rift Valley bordering Israel and Jordan constitutes one of the classic examples of evaporite deposition in action as shown in the PowerPoint. It is not only a great commercial place for its salt content, but a famous tourist center and a health resort, where tourists can be seen reading newspapers while floating in Dead Sea water, because it has 6 times more salt content than the average ocean water, or covering themselves in salt rich Dead Sea mud as a therapeutic and beautification cure. However, the deepest and the saltiest depression in the world is Lake Essel, which is 10 times saltier than the ocean in Djibouti. Evaporite deposits at such places include, apart from salts, important materials of magnesium, bromine, and have been commercially exploited for centuries. Apart from being an economic source, evaporite deposits, in particular the ancient deposits, help to interpret the past climatic conditions and a special kind of environment which could be mind boggling. For example, to produce 1 meter of halite requires evaporation of around 60 meters of sea water. At this rate, 1000 meter thick halite bed at Stassfurt in Germany, as shown in the PowerPoint, would have needed evaporation of saline water from a basin many kilometers in depth. Naturally, what conditions existed to produce the ancient evaporite beds in the geological past are not operative today on that scale and dimension. There are certain important differences between the ancient and the modern evaporite beds. Modern evaporite beds have very limited extent. One of the largest evaporite in Western Australia, Lake McLeod, has 9 meter of Holocene salts deposits and measures 100 into 50 kilometer only, while Miocene Messinian Mediterranean basin is extremely large, around 2400 to 600 kilometer extent of the huge Permo-Triassic salt basin in Europe, including Stassfurt and gypsum beds of Rajasthan are also equally larger and shown in the PowerPoint. Evaporite deposits in Sabkha environment is somewhat different. An Arabic word Sabkha or Sabka constitute a supratidal environment of deposition, barren and desolate, with evaporite flats lying above the high tide level in arid or semi-arid regions. Crucial coast of Arabia, Abu Dhabi, Persian Gulf and Gulf of California are the type areas. Evaporite deposition is dependent on the local water table. In Sabkha, features in sedimentary strata are indicated by evaporite deposits, pebbly conglomerate, mud cracks, absence of fossils are among such features. Salt beds buried under thick sediments are liable for plastic deformation under pressure and will rise through overlying sediments as salt domes and are known to be good oil traps. We shall deal metamorphism as ore forming processes and specially what we call metamorphic deposit. Metamorphism acts in two ways, producing ores that are called metamorphic and metamorphosed. Ore elements already present in the host rock will be converted into ore minerals under the influence of metamorphic agents and are termed metamorphic deposits. Agents that are bringing about the ore formation from the constituents of the existing rocks are heat, pressure, time and possibly fluids. But unlike in contact metasomatic deposits, ore components are not introduced from outside the host rock. Majority of ore deposits are of non-metallic category and include graphite, aluminosilicates which are kyanite, andalusite and sillimanite and dumortierite, asbestos, talc, soapstone, pyrophyllite as also emery and garnets. Space will not permit to cover all these deposits, hence only graphite and the aluminosilicates will be dealt in sub-interest. Sedimentary rocks that had sufficient bituminous matter in them become the host rock to develop graphite due to regional metamorphism. Ancient metamorphic rocks like schists and gneisses as also crystalline limestones in many parts of the world host graphite as beds, embedded masses varying in grade from 5 to 10% of the rock mass. South and North Korea are the major producers, while important deposits of graphite are found in Siberia, Austria, USA, Mexico, Serbia, Croatia and Sri Lanka. Graphite has a wide occurrence in India, especially the khondalites, which are ancient metamorphic rocks rich in selenite and garnet of Odisha. Has very good deposits at Patna, Kalahari, Koraput, Atammaluk and Sonpur districts. The same rock types also host graphite in Andhra Pradesh in East Godavari district, Vishakhapatnam and Krishna district. Most of the states like Kerala, Karnataka, West Bengal and MP, which have vast tracts of old metamorphics, have graphite deposits, though not all of the same size and grade. Kyanite, andalusite and sillimanite. The first three, which are the best example of polymorphs, have a composition of Al2SiO5, are very important members of regionally metamorphosed aluminous sedimentary rocks and one of the best examples of polymorphism as shown in the PowerPoint. Andalusite is particularly characteristic of thermally metamorphosed rocks. Kyanite is much denser and therefore is restricted to conditions of extreme pressure. Sillimanite is the commonest of the three and most stable of all. It is preferred at the highest temperatures and is therefore characteristic of innermost zones of contact metamorphosed sediments. All of them constitute a very important source of refractory raw material. The most important deposits of sillimanite in India are from Khasi Hills region of Meghalaya, including the one at Sonapahad. In biotite, sillimanite, cordierite, quartzite is the product of high grade metamorphism of pure clayey rocks associated with granite and granite gneisses. Other promising sillimanite deposits are from Madhya Pradesh, Pipra in the Rewa district, Bhandara district of Maharashtra, and garnet sillimanite gneisses from the southeastern areas of Kottayam and Ernakulam district of Kerala. USA, Kenya, South Africa, Canada and Mozambique are among the chief producers of these deposits, and India has one of the best deposits of kyanite and sillimanite in the world. In Jharkhand area has several kyanite beds which are found in a zone of 125 km long belt along the Singhbhum thrust zone. Among these, Lapsaburu in Kharswan is of the world fame, hosting kyanite in kyanite quartz schist rock. There are several other important occurrences, including the one at Ranchi in West Purulia district of West Bengal, Nellore, Khammam, Dungarpur, Ajmer in Rajasthan and Hassan district in Karnataka. We have sufficient kyanite deposits, though not as good as the one at Lapsaburu. South Africa is the leading producer of sillimanite in the world. Australia, India and Ceylon are the other important producers. Other metamorphic deposits include talc, steatite, asbestos, serpentine, pyrophyllite, emery, garnet and titanium ores. Time and space will not permit to deal with them presently. Though not falling in the category of an ore mineral, marble is perhaps a very common and useful commodity which is the product of metamorphism of pure and impure limestone and dolomites. Coming to module 5, we will deal with metamorphic deposits which we called metamorphosed deposits. Metamorphism of rocks and the ores that are in them are inevitable for changes once they are buried deep enough with increase of temperature, pressure and chemically active fluids. New set of minerals assemblage and structure develop. When the ore minerals that were already formed by early processes, namely igneous or sedimentary, they are subjected to higher pressure and temperature conditions, as a result of which they become tough and hard and quite often attain a better grade. Such deposits are called metamorphosed deposits. Banded iron formations BIFs and Precambrian manganese deposits are the best examples. We have already learnt about them and their distribution in the lesson dealing with sedimentary iron and manganese ores. Practically any kind of deposits, especially those of the Precambrian age, have undergone different degrees of metamorphism. Thus, it has definitely affected the country rocks and also the ores that lie within them. Thus, be it the world's famous stratiform lead zinc deposits of Broken Hill, Australia, which is subjected to repeated deformation and metamorphism, or the Witwatersrand gold uranium deposit in South Africa, or the apatite bodies in Siberia, or the pyrites from the Urals and hosts of others in different parts of the world, including those of Singhbhum sulphide deposits, Ambamata polymetallic sulphide deposit in Gujarat, have also suffered considerable degree of metamorphism, and there are imprints clearly visible on them. Though not falling in the category of an ore mineral, marble is perhaps a very common and useful commodity, which is product of metamorphism of pure and impure limestone and dolomites. Hope you have enjoyed this lesson, which culminates all the processes of ore formation, whether primary or secondary in nature. Thank you very much.